Okay. Hello to our friends from around the world. I am Mona Masafi, a research fellow at the Mayo Clinic and your moderator for today's webinar. Welcome to this month's AI webinar, Uncertainty Quantification, a way towards trustworthy deep learning in medical imaging. Thank you to the SIIM Machine Learning Education Subcommittee for the organization of this webinar. Okay, just a few housekeeping points. SIIM members, this webinar is eligible for 1 hour of SIIM IIP credits that can be used toward your ABI SIP certification or recertification. SIIM SIP members, if you would like to take advantage of our automatic credit transfer, be sure to include your date of birth and ABI ID in your profile when renewing your membership, please. Okay, please, next slide. Please add your questions using the Q&A icon on the Zoom menu throughout the webinar. We will work to answer them all of your questions, hopefully after the talk. Okay, next slide. I want to say that I'm very excited to be here alongside my amazing colleagues. We have Dr. Richard Bruce here with us, Associate Professor of Radiology, Vice Chair of Informatics at the University of Wisconsin-Madison. We have Dr. Bradley Erickson with us, Professor of Radiology and Director of AI Lab at the Mayo Clinic, Rochester, and Dr. Shahriar Farghani, postdoctoral research fellow also at Mayo Clinic AI Lab in Rochester. So without further ado, I just want to start the talk. We're going to have this webinar in a way that encourages a bit of discussion and is more interactive for everyone. I will ask our expert speakers a few questions so that they help us understand the concept and also use cases of uncertainty quantification. And my first question will go to Dr. Erickson. Dr. Erickson, I want to ask you for understanding a bit of a concept of uncertainty. We know that nearly all, or if we don't want to say all, most of the commercial AI tools, they provide us a binary output. For example, we give them an image, they say that they have this or not have it, and they don't actually indicate how certain they are about the prediction that they're making. On the other hand, we see in medicine and we see in radiology a lot of uncertainty. In most reports, we see a differential diagnosis. I want to know, can you please kindly tell us about why is AI so different with how the real clinical practice is implemented? Can you please let us know?
Yeah. So, when an AI produces a prediction, it does actually have internally a number. The number actually typically is the output of what's called a softmax function, which is really optimized for helping the algorithm train well. It looks like a percentage, but it's actually not a percentage probability. And so that's the first important thing for people to understand is that, yeah, there is a number underlying a prediction, but it's not actually anything close to a certainty level or probability level. And most of the tools that are out there today are triage tools that basically just resort the interpretation work list, and they may or may not produce a thumbnail image saying, here's the thing that made me pop it to the top of the list. But they don't usually say, here is the part of the image that looked like pulmonary embolism, and I'm 33 or 93% sure. But also the probability is different from certainty. And probability, if it's properly calibrated, is going to reflect the probability based on that calibration set. And that's actually, to do it right, needs to be separate from your test set. But then again, the uncertainty prediction can include other things like, gee, this doesn't look like any image I saw in my training set, or it looks like a lot of things in my training set and I have a high confidence. And so that's some of the nuances that we sometimes bypass when we think about implementing these tools into clinical practice. But the reality is that most radiology reports do have some language around certainty levels, like, this is highly consistent with X, or this could be consistent with, and that reflects the certainty level. Now, a problem, of course, is that those are words, and we humans don't necessarily have the same mathematical boundaries around, highly consistent with. Does that mean 99%? Does it mean 95%? And so, that's still a limitation in how we would translate some of these certainty measurements to clinical practice. But I think that is the real world of clinical practice, is that there's always a degree of uncertainty for various reasons. And it's critical that we start to think about how to approach that with the AI tools that we develop and deploy.
Thank you. Thank you so much. My next question, Dr. Bruce, can you please tell us how uncertainty quantification can impact the use of the utilization of models in radiology practice? I want to know, can you highlight a bit about the applications of UQ in the field, medical imaging or radiology?
Sure. Yeah, so I think, one of the things that's always interesting is the concept, when someone builds a model, you're really testing it in what, no matter how much effort you put into sort of assembling different training data sets, validation data sets, what you encounter in the wild may differ significantly for that. And just one of the realities of radiology and medical imaging in general is that there's a huge diversity of data. And that there's a lot of reasons for that. They may be technical factors. There's differences in scanner types. There's all kinds of protocol differences. And above that, humans are not all the same. I mean, that makes me recall a conversation, several years ago with a vendor who was really perplexed as to why there were differences in acquisition protocols. And ultimately, it came down to, you realize that humans are not all the same shape, like, right? And so that just at baseline affects a lot of different things. And there's a really famous quote that's been circulated widely by Andrew Ng talking about, the brittleness of AI, how you can develop something, have it work in one environment, and then it's very difficult to maybe translate that and have it have the same performance at the hospital down the street. And so, I think that is often seen. And, while AI has been huge over the last several years in the radiology space, there's still a lot of immaturity. And so we have encountered a number of different commercial AI solutions that in the process of either implementing them clinically or evaluating them for implementation, we've seen different performance, which is somewhat perplexing at times. And I think when we talk about uncertainty, that's really what we're getting at, is that when you have an algorithm that really just has a binary output, so those triage algorithms that Brad mentioned, where something is really either positive or negative, if you get results which don't seem to make sense or don't seem to always match up with what you expect, since we don't have any other information to go on, as a radiologist, you very, very quickly lose confidence in the output of that algorithm, and you don't necessarily know why it might be giving the wrong answer. And so to give a very, very concrete example, we had a commercial brain imaging algorithm that was implemented, and we saw just unexpected output from it in that it would give it had a much higher rate of incorrect output than what we would expect. And so that started a back and forth communication and exchanging data sets and information, with the company that we were working with. And we learned a lot from them, and hopefully they learned a lot from us. And so there was, they had assumptions about what the nature of the data was that they were receiving, that, every exam was going to have exactly the same, angulation in terms of patient positioning, all of those types of things. And there's no way built into their algorithm to output anything other than basically a positive or negative result. And so there wasn't a way for their algorithm or their user interface or the output produced to say, hey, this doesn't quite match up with the data that I'm used to seeing, or any of those things. And so there is a need when being on the receiving end of some of these to have a better understanding of where is the failure, because that will ultimately really affect the confidence that you have in the output being produced.
Thank you so much for your answer. I a lot learned from that. Thank you, Dr. Bruce. Anna, can you please start the first poll for our audience to see what they think? Yes. The question is that with what we said, we mainly talk about classification. My first example was about an image, thinking, for example, is that a pneumonia, not pneumonia, or being a classification task. I want to know what you think about other tasks. Can UQ be applied to them or not? Okay, can you all see the results? I'm seeing them. Okay. Most of our audience, 70%, 70 to 75, they think that for object detection, segmentation, image generation, for all of them, UQ can be applied to, other than classification. With that in mind, okay, Dr. Farghani, my next question is for you. I want to know if you can talk about each of these, for example, not each of them. Can you talk about the other areas? And also mainly, I want to know what tools do we have? What ways do we have to measure the uncertainty? Can you talk about that a little?
Sure. So let me start with the first questions about what are the tasks that we can apply UQ on them. So as Dr. Erickson mentioned, essentially when we do classification, we output a number at the end, right? And then we turn this number into a class, right? So we can think of this as if we have infinite classes, then our task would be regression, right? So basically, we're gonna predict a continuous variable. So in this sense, we can apply UQ to regression tasks because essentially it is the same concept, right? So with the same mindset, we can think of, for example, segmentation as a classification task at the pixel level, right? So because essentially what we do during segmentation, we're assigning a specific pixel to a specific label, right? For example, if we're going to do a brain segmentation, we're going to assign a specific region to temporal lobe, right? So essentially, we're going to do a classification. So still UQ can be applied to segmentation. When we're doing image generation, essentially, we're doing a lot of regression, right? Because essentially, we're generating new values for each pixels, right? And then again, we can apply uncertainty quantification to the image generation task. So in this way, essentially, we can apply UQ to all the medical imaging tasks that we're working with. So I guess this was to your first question. For the second question, what are the ways that we can quantify the uncertainties? I mean, there are many ways actually that we can do UQ or uncertainty quantification, but traditionally we can categorize them into three main categories. The first one, and obviously one of the most one of the simplest one to understand is ensemble. So essentially we can create multiple instances of a same model, and with slight variations. How? For example, we can train different models from different start points, right? So we expect that all the models at the end converge to a specific point, but with a slight variation, right? So essentially, we will have several variations of the same model, right? And then during inference, when we input the same image, we expect that we will get the same results, but again with a slight variation, right? And these variation could be used as an indicator of the uncertainty of the prediction. So if we see a large variation in the prediction, it means that these input doesn't fit well into this model, right? Because even a slight variation in the model will lead to a huge difference in the final output, right? So this is the basic idea behind model ensemble. The second method, in general, they're called Bayesian methods. So I guess most of the audience are familiar with Bayes' theorem, which is essentially the conditional probability. So it says that if you change one of the parameters of the model, and if you change these parameters in a systematic way, probably you can see the distribution of the predictions as opposed to a single prediction, right? And the uncertainty quantification is all about quantifying the distribution of the prediction, right? So essentially, if you change the parameters, you'll see some changes in the final prediction, right? And again, one of the most famous methods in this group is called Monte Carlo dropout, which is based on dropout concept. And I guess, again, most of the audience are familiar with dropout when we are doing this during training in order to avoid overfitting. Essentially, we can turn off some of the nodes in our neural network in order to avoid overfitting. But if we can do the same thing during inference, each time if we turn on and turn off some of the nodes randomly, then we would get, again, slightly different predictions, right? The same idea as the ensemble. But the difference here with the ensemble is that for ensemble method, you need to train multiple instances. But for Bayesian methods, you need to infer multiple times with a single instance. So it's more computationally efficient, but the idea is still the same, running multiple instances, right? So this is the second way. So far we've talked about ensemble and Bayesian methods. And the last one is called evidential deep learning, which looks at the classification problem or whatever task that we're doing as a kind of evidence gathering process. So if you gather more evidence, then you'll be more confident in your prediction. And the claim of these method or evidential deep learning is that the output probabilities would be calibrated. This is the claim, but the claim is the output probability are going to be calibrated. And again, it's going to produces some numbers that essentially a higher order probabilities that you can get directly the uncertainty out of those higher order probabilities. So these are the main common uncertainty quantifications, but I guess there are some more methods which probably we're going to discuss them later.
Okay, thank you. I really like the categorization explanation. Thank you so much. The other question, Dr. Erickson, can you please tell us if you said that there are different way of thinking, radiologists and machines, they think differently, sort of, but is there a way that we establish a connection between the uncertainty reported by radiologists or annotators in general and how the model uncertainty works? Can we connect them?
So I think that that's probably a work still to be done. I think certainly at a conceptual level, they kind of make sense, right? If uncertainty measurement comes out and it's 99% certain I have a pretty good idea what that is versus 50% or 5%. I think, the perhaps next level of technology or next level advance on that is to start to put human words onto those probability ranges and to understand, well, this is what is typical in clinical practice. I think that's something we don't have a good handle on is, when a certain finding is present, what does that certainty level mean? And probably that is going to be a geographically dependent, population dependent sort of thing, because the pre-test probabilities are going to impact the post-test probabilities, and we all see different populations and therefore are going to see different pre-test probabilities. So, I think even that is going to be a challenge to implementing uncertainty in a universal, identical type of fashion, as that's probably not the way reality works.
Okay, thank you. Thank you so much. Dr. Bruce, as we move forward in this path, can you tell us a bit of challenges that you see in the future for uncertainty quantification in medical imaging? Can you think of any challenge that will happen?
Yeah. Well, I think we can take it through a couple of different potential categories. One of them is and there are some kind of funny examples. When you look outside of medical imaging, early some of the early, hilarious things that turned into memes were, different images like fried chicken looking like different types of dogs and AI not being able to differentiate. When you apply the same kind of principle to medical imaging, we've seen, different people do some things the same, either with sort of intentional attacks, if you will. I would, where you're just trying to fool the AI. And so, as an example, at an ACR meeting, someone brought up that they had used a pickle and done a mammogram of a pickle and received an output that there was a high probability of cancer within the pickle. And so, one of the challenges, and so the challenges all sort of point towards either a robustness challenge in terms of how we design the bounds and the pre-processing so that there's sort of more there's more quantification about, do the inputs line up with what's expected, before going into a model or as part of the model. And then we also have significant output challenges. And one of the big ones is, and it sounds mundane, but there are not great ways to convey discrete information, across different platforms. And so, as Brad mentioned earlier, most of the models out on the market are triage type algorithms. And so the outputs of those models are oftentimes just raising or lowering the priority of a given exam, or potentially, producing some output that goes into packs. But there aren't great ways to surface more discrete data, whether it's measurement data, whether it's segmentation data, or uncertainty data, or error type data, so the algorithm, even if it had the information about uncertainty or errors available, there isn't a way for it to communicate to downstream systems that, hey, we think that there is an input out of bounds challenge, where the algorithm received this data, it processed it, but it doesn't line up with what was expected. Or for conveying, even an uncertainty score. Yes, we predicted that this abnormality is present, but there isn't a mechanism for us to surface that in your PACS or in your EMR, to make that available within Epic. And so those are kind of plumbing type changes, but they're nevertheless very important. And oftentimes the implementation can be, as challenging to designing, real workflows and the tooling and machinery around it as the core algorithm itself.
Thank you. Thanks. The next question I want to ask Dr. Faloni, is there, now that you speak about ways of measuring uncertainty, for example, we got out of a model that this model is 0.2%, 0.2, no, 20% uncertain, for example. Is that a meaning to that? Does a model with uncertainty quantification implemented in it, does it give this sort of numbers, or does that mean, can you elaborate on the output a bit?
Sure. So, there are many ways that you can report the output of your UQ method, right? And today, there is no standardized way of doing that. And that's one of the other challenges. So essentially, some people report the variance of the predictions as an indicator of the uncertainty. So it could be then a single number, and which won't be a percentage. It could be, for example, 2.5, right? And it shows the variance of the predictions, right? And probably you know that the variance itself as a number doesn't have any specific meaning, right? You should know the distribution. And again, you need to then add some more calculation to it to probably try to interpret that specific number, right? So one way is to report just the variance. The other way is to report to some of the other people apply more sophisticated methods, or like they apply Shannon entropy on the outputs to convert those output numbers into some more meaningful terms, but still those numbers, 0.4, doesn't have a specific meaning, and at least it doesn't have any clinical specific meaning. And again, as Dr. Erickson mentioned, if it says 0.4, you can be sure that, okay, this is an uncertain case or this is a certain case, right? So one way to get around these problem is you can do sensitivity analysis on the outputs. So in this way, for which again, if you want to do sensitivity analysis, that should be case specific, and that should be task specific, and that should be situation specific. For example, if you want to apply this on a screening model for example, pneumonia detection on a specific hospital, then you need to do the sensitivity analysis, and then you can pick a threshold that based on that threshold, you can say, okay, if the uncertainty output is bigger than 0.4, then I would consider this case as uncertain case. Probably it needs a second look by a radiologist. Or if it is less than 0.4, I would trust the model. It is a confident prediction. I will trust that, okay, no need to second look, right? So again, but if you want to apply these methods, you need to tailor it for each task, for each use case, and for each setting, right? And again, as an example, if you want to apply the same type of model, one for screening, one for confirmation, these thresholds should be different, right? So in other words, for each model, then you can convert those numbers to some English terms, right? Like highly possible, etc. But this is one way that I guess it is the most common practice in UQ literature. But there are some more newer methods that provide some statistical guarantee to the output, and they provide some meaning to the numbers. And there is a family of methods which in general called conformal predictions, that they provide a statistical guarantee to the outputs of the uncertainty quantification. What do I mean by that? For example, if they say, let's think about a regression task, which is easier. For example, if it says, imagine that we're gonna predict age from a hand radiograph, right? If it says it is between 4 and 5, then it can provide a statistical guarantee, which means that, okay, if it says between 4 and 5, in 90% of the cases, the actual prediction will fall in between 4 and 5, right? The same thing could be applied to the classification test. And the good thing about classification tests by using conformal prediction is that it can provide a differential diagnosis list rather than a single prediction, which is more closer to what we're doing as the human. And the length of the differential diagnosis list could be an indicator of the uncertainty. So again, still to date, there is no standardized way of reporting the uncertainty, but I guess the newer methods like conformal predictions will provide some more meaningful way of reporting uncertainty and probably more clinically useful of reporting the uncertainty.
Thank you. Thank you so much. We are going to move to others' question, but just before that, I have a personal question. Do you think that uncertainty quantification can sort of help the explainability also, or is that a completely different beast? Is it possible that they help each other?
So I think it's definitely related, and it would be a component of explainability. When we look at AI doing things which aren't classification tasks, so segmentation, in my mind, is a great example of this. Oftentimes, we QA segmentation in the form of output is produced where if you we don't just blindly accept quantitative numbers that come out. There's oftentimes an imaging data set that's produced that you can look at to basically QA and the output from the AI, and that is a form of uncertainty quantification in and of itself. So the difference in a pure classification task where your output is essentially binary is, we don't necessarily know, what in detail it was that affected that prediction. And so to me, it's just providing extra context. So, one of our Q&A questions is about kind of that same concept, and how do you is it just going to cause alert fatigue? And that really gets to there's a lot more to AI than just the models itself. It really is how does the entire workflow work? And so to me, if I'm confident in a case, I may or may not feel compelled to even pay attention to AI output. But if I have an internal level of uncertainty, you'll see, patterns in radiologists. I might start really scrutinizing the chart. Okay, something is a little off on this patient. What else is going on in their history? And that may dramatically affect, what I think is happening. And so to me, uncertainty quantification, if you have an uncertainty score that's coming across with a binary classification, that's just additional context to me. So if I see, okay, well, it thinks that this is X type of tumor or whatever the algorithm happens to be, but the uncertainty score is really high, then that lets me temper, what I think is coming out of the AI.
Thank you. Thanks. That explains a lot. Thank you. Let's just one other thing. What about bias? Do you see a connection between uncertainty quantification and reducing the bias in the model as well? I think you sort of covered, but
yeah, the bias, I think there's a lot of different ways to that bias can influence a model, and to me, it's all about context. And we don't, oftentimes we don't actually know the ground truth about how there might be differences based on any number of factors in different populations, for an underlying disease process. Brad alluded to this earlier with comments about pre-test probability, post-test probability. And when we get right down to it, when biases in different subgroups is really about oftentimes, pre-test, post-test probability. And so when we say that an AI algorithm may be biased in one category or another, it's because we either don't have enough data to know what those underlying pre-test probabilities might be, or that there are differences that aren't accounted for in that model. And so hypothetically, and it really would depend on the individual use case, you would want to be able to, that's the whole point behind uncertainty quantification, is that when there may be differences in input data, that you have some way of surfacing that. So if these images are coming from a population where there may be underlying factors that weren't accounted for in the training data, that the uncertainty quantification would be higher, and that would clue me in that, oh, this algorithm may not be the best algorithm for this input.
Thank you.
Yeah, and just to piggyback on that, at the conference that Dr. Bruce referred to with the FDA, one of the inciting events for that was when an AI made a prediction of a stroke, but actually what happened is that the patient moved a bunch in the CT scanner and the AI tool predicted a stroke. And because there wasn't any measurement of, gee, all that motion doesn't look like anything I saw in the training set, because it was a nicely curated data set of, good, clean head CTs, the prediction came out, oh, there's a stroke. And so, to get to some of the questions that I see about clinical application and such, I think that may be one of the more straightforward things, is just to say, this doesn't look like any of the data I saw. There's a question by Raim Geis about, automatically identifying the position of an ET tube. Well, if the patient moves a lot during that acquisition, the AI may say, oh, the ET is, down in the stomach. Well, it probably isn't. But if the patient moved a bunch and you don't have something like a UQ tool to say, this is really very different from my data, so don't trust my prediction, don't act on it. And I think that, some of the questions then are, well, what threshold should it be? Is there going to be alert fatigue? Well, that's where we have to, I think, advance the science more of uncertainty quantification to say, okay, now I know what a value of 0.5 means, or I know what 0.8 means. And, if it's above 0.8, that's really pretty certain that it's making the right prediction. 0.5 is I don't know, or, 0.5 or less. So that's where we still, we're not, I don't think we're close to having widespread adoption in the clinic. I think, to my knowledge, there are no commercial products that have this in it. I'm not sure if there are even non-commercial products, university developed AI tools that are deployed clinically that have UQ in it. And so I think we're still pretty early on in the development of this, but I think that's the trajectory that we're on, is, once we get a handle on a good way to calculate this uncertainty measurement, we will then have some sort of calibration of, 0.8 and above, you can pretty much take it to the bank. 0.5 to 0.8, yeah, you probably should have a human look at it. 0.5 or less, completely ignore the prediction. Or, and again, I don't know exactly what the scale is, but I think that's probably the next pathway for UQ.
In the absence of a way to quantify uncertainty, the debate today oftentimes with clinically implemented algorithms is, do you need a human in the loop, or do you surface output directly to kind of the end the end providers, and that's and so especially when you have something where the output is not necessarily binary, do you need someone to take a look at this and say, this is valid output or it should be ignored? And the FDA last summer issued the letter that was kind of aimed at that, with stroke algorithms, and the worry is that if you don't have some way, either algorithmically or with a human in the loop, that you could end up having erroneous predictions based off of faulty input data, artifact, patient movement, technical factors, et cetera, that end up getting a patient into a situation where someone may act on output from an algorithm that causes harm to a patient. So the stroke example is, I think, the ideal example for that, to where you could be taking a patient to go do a stroke intervention when someone who has knowledge in the field would look at that output and say, this is not consistent with a stroke, this is consistent with artifact.
Thank you. Thank you so much. We have a few questions, I think, about the best way of measuring uncertainty. I think that was sort of covered, but if you like to talk about it, Dr. Pagani, they ask you about what would be the most optimal for, I know that this case relevant. And also we have 2 raised hands. I don't know if it's okay. Dr. Pagani, can you please answer this question, and then I will go to attendee.
Sure. So absolutely. I guess still there is no comprehensive comparison between different methods and on a benchmark data set. So again, one of the reasons is that there is no good benchmark data set for doing UQ. So if there is no good benchmark data set, so the methods cannot be compared together in a fair way. But still, I guess it depends on the use case. But as I said, to me, conformal prediction is the way of probably doing is the way of doing uncertainty quantifications, because as opposed to the other methods, it can provide a statistical guarantee associated to the numbers and to the sets. So probably conformal prediction would provide more realistic information about the models, and you could be more certain about the uncertainty quantification.
Okay, thank you. Thank you so much. I found out that we cannot, sorry, audience cannot speak in this webinar, and I really appreciate if you write your question in the Q&A. I make sure that I read them. The next question from Dr. Khaled Yunus is that what are the current FDA guidelines or expectations regarding uncertainty quantification for AI-driven medical devices? How does the FDA view the role of UQ in the pre-market approval process for AI/ML-based medical imaging tools?
Yeah. So,
go ahead, Brad.
So I haven't heard the FDA mention anything specific about uncertainty quantification, and of course, I think they tend to be reluctant to provide specific guidelines of saying, do this and you will get approved for obvious reasons. But to my knowledge, I haven't seen any specific language around UQ requirements in medical products and how they would think about approving them. I don't know, Richard, if you have.
Yeah, I would echo the same thing. I mean, in terms of my understanding, and I think I certainly won't claim to fully understand the FDA's process, but in general, in this domain, things fall into 2 different categories. Triage versus computer-aided detection or diagnosis-oriented, and so the kind of the burdens for evidence vary between those. And so if you look at some of the FDA submissions on the triage side, I think one of the first reactions that folks often have is that the number of sort of testing data sets seems rather small, and that is oftentimes because the burden there really is that you just have to show that that performance of a radiologist or in a workflow can be improved by in terms of in terms of time to diagnosis or things like that, versus you have to show that there is improvement in rate of diagnosis, and the bar is much higher when you are using a tool that's not for triage. And so but in terms of how the results are communicated, I'm not aware of any guidance from the FDA that says, here's the context of the data that has to be communicated. And I think that in large part, as you can imagine, there's lots and lots of different ways that AI and machine learning manifest themselves now in the imaging chain. And we are very focused in most cases on kind of the inference, classification, detection of disease in AI. But if you look at the entire imaging pipeline, there is AI that gets applied all the way from ordering to scheduling to image generation on the modalities. I mean, probably the biggest use of AI that I'm aware of, even if you were to look at most institutions, many modalities use AI now as part of the image generation itself. And so if you were to ask someone, what percentage of medical imaging exams use AI, in some places you may be approaching 100%. And that there isn't, that's a very different sort of task, but and so the FDA guidance as to what approval criteria looks like in those tasks versus where you're making a diagnosis is quite different.
Thank you. The next question is that if you have significantly unbalanced data, does that change the way you measure it or what you might do with it?
Maybe I can take this. I guess one of the, application of UQ would be applying this methods when you have different training data set and different test data set. And what we see in actual practice is that oftentimes the training data set is different from where we're going to deploy that model, right? And so essentially the UQ will help that. So first, to answer directly to the questions, no, it's not going to affect the way that we're going to apply it, but it's a way that we can identify the domain, the distribution shift. Let's put it in this way. So if we have trained it on an unbalanced data set, and then we are going to deploy it in another unbalanced data set, but with different population structure, probably the role of UQ would be flag the cases which are not similar to our training distribution or to our training set. So by flagging those cases, we would focus and we would be certain about the cases that we have kind of had the similar cases in our training set. So again, it's not going to affect the way that we're going to apply UQ, but UQ is the way to help the problem of unbalanced data set and distribution shift.
Okay, but is there a way, is there one of these categories that you could say that would be the best to use when we have very unbalanced data? Or so it's no different?
Again, the same question as before. What is the best way? But let me mention one more thing. Some of these UQ methods, you should apply them during training, and some of them are post-hoc methods. For example, for having an ensemble model, you have to have you have to have different models, so you need to train different models.
Okay.
But for instance, the conformal predictions is a kind of post hoc method, model agnostic, task agnostic method. So you don't need to train anything again from the scratch, but particularly for conformal prediction, you need to have a set from this target distribution, from the target population, which we call it calibration set in conformal terminology. And you need to use that calibration set to kind of recalibrate your model. And these recalibration is kind of different from calibrating the probabilities. These are similar words, but different concepts. So in order to apply these post hoc methods, you don't need to train the models again from the scratch, but you need to have a sample from your target distribution.
Yeah, and I wonder also if a part of the challenge with a significantly unbalanced distribution is that it implies that the small class, whatever that is, you probably don't capture the complete distribution of samples in that limited population. And so as a result, most likely something like a UQ, like a conformal prediction, you're going to have much larger bounds on your prediction just because you don't really understand what that class is all about. You know, if it was mismatched, but you had 1 billion in the low class and 100 billion, and that billion examples really characterize the population well, we probably wouldn't be as concerned about it. But if you've got 20 versus 2,000, 20 most likely doesn't capture the distribution. And so it's probably that aspect of imbalance that then drives how uncertainty quantification would give you large bounds around that minority class prediction.
Thank you. We have also one comment about the FDA from Dr. Younes that FDA requires clarity of the intended meaning of the numbers that's submitted as a confidence level of the output. Sometimes that requires certain mapping to what the clinicians should understand from these numbers. Which is, I think, correct. Do you want to talk about it, or should I move to the next question? Okay, the next one is that in the context of medical imaging, could you share insight of the role of Bayesian deep learning and Bayesian neural networks in quantifying uncertainty? How have these methods contributed to the trustworthiness of deep learning models, and what challenges or limitations still need to be addressed in their implementation within medical practice?
I guess we have covered part of this question. So Bayesian neural networks are the networks that fit into the second category that I mentioned, Bayesian inference in general. So essentially, again, the way it works is you can tweak some of the parameters and you can see how the final predictions will change. And the amplitude of that change would be a kind of estimate of the uncertainty of the model. And in general, all of these uncertainty quantification methods would lead to trustworthiness of the model, because essentially the UQ is all about forcing the model to say, I don't know, when they really don't know, right? So if a tool say, I don't know, so then these tools should become trustworthy, right? So you can trust on it, because when it doesn't know, it would say, I don't know, right? So again, this is the whole idea behind the entire UQ.
Thank you. And we have one other question from Dr. Faghani that among the techniques that you described, can you comment on whether they can predict accuracy as well?
So let me put it in this way. What we are trying to do in uncertainty quantification, we will get the output, right? So the output itself would be an indicator of the model's accuracy. So we're not trying to manipulate these output, but essentially we're gonna build a bound around these outputs, right? So we're gonna assign a kind of confidence interval around these outputs. So again, the assessments of the accuracy is something different, that we're going to do this before uncertainty quantification, but essentially uncertainty quantification, we're going to build a confidence interval around the prediction, and we'll assess that confidence interval.
Okay, thank you. There are a few questions, but I'm not sure how much they're related to uncertainty. One of them is that, is it possible that AI could be more effective in imaging workflow assignment, for example, sending reading tasks to the best doctor based on past reliability in finding positives and image characteristics?
I can take that. I think the overall challenge in something like that is that while there are a large number of studies, we don't have anything that I would say even approaches the level of data that you would need to be able to assess that and build a model to do assignment on. And medical imaging volume today, I think across the country and probably across the world is extremely high, and so most radiology practices are sort of struggling to keep up with volume, and what we deeply leverage auto assignment internally, but that it's mostly to assign and level workloads across different radiologists and groups, and to smooth things out. And it is heavily weighted towards what people's interests and subspecializations and shifts that they take. But to directly address what you're getting to, we don't have any way of sort of quantifying directly who would be the best radiologist, say in our practice to read this particular type of study with this pretest probability of a certain condition, and things are much more continuous than that, because a lot of studies, a binary diagnosis is not necessarily the hard part. The hard part is figuring out, okay, what's the level of importance of this and what needs to happen next. And so diagnosing a brain tumor is relatively easy. 4 or 5 or 6 studies into their treatment, knowing does this patient need to go back for resection or change their chemotherapy agent, is a very different question.
Thank you, Dr. Bruce. I think we reached the end of the time. I really want to thank you all. And I'm not sure if we have the time for the second poll, and we answered the question completely with clarity. I want to really thank you, Dr. Bruce, Dr. Erickson, Dr. Faghani. Thank you so much for your time to talk on this very critical topic with a lot of potentials for working on it. I just want to, if you have any last words or you want to add something, please let me know. If not, I just want to tell you that if you like this topic and or want to see something AI related, we want your feedback. The session survey will pop up at the end of the webinar, as well as will be included in the post-webinar email as well. I want to thank you all. There's still also, I want to tell you that there is a call for research about applied informatics abstract to the SIIM 24 annual meeting. Please make sure to send your abstracts by December 15th deadline. That's all. Thank you everyone for attending today's webinar. I hope that you all have a great rest of the day. Thank you so much.
Thank you.
Thanks. Bye.